Welcome to the Data Center University course on Data Center Project Planning, Establishing a Floor Plan. For best viewing results, we recommend that you maximize your browser window now. The screen controls allow you to navigate through the e-learning experience. Using your browser controls may disrupt the normal play of the course. Click on the attachments to download supplemental information for this course. Click the Notes tab to read a transcript of the narration. At the completion of this course, you will be able to define a data center floor plan, discuss floor planning concepts, including structural room and equipment layouts, describe the effects of the floor plan on data center performance, review basic principles of both equipment layouts and structural room layouts, identify the floor planning sequence, and avoid common errors in equipment layout. A data center floor plan includes the layout of the boundaries of the room and the layout of the IT equipment within the room. Most users do not appreciate how critical the floor layout is to the performance of a data center, or they only appreciate the importance of floor layout after a poor layout has compromised their deployment. A floor plan strongly affects the power density capability and electrical efficiency of a data center. Yet many floor plans are established through incremental deployment without a central plan. Once a poor floor plan has been deployed, it is often difficult or impossible to recover the resulting loss of performance. The floor plan either determines or strongly affects the following characteristics of a data center: the number of IT rack or cabinet locations that are possible within the data center, the achievable power density, the complexity of the power and cooling distribution systems, the predictability of the temperature distribution within the data center, the electrical power consumption of the data center. Many users do not appreciate these effects during the data center planning phase and do not emphasize their floor layout early enough. The result is that many data centers unnecessarily provide suboptimal performance. The purpose of this course is to explain how floor plans affect these characteristics and to prescribe an effective method for developing a floor layout specification. Floor layout plans must be considered and developed at the appropriate point in the data center design process. Considering floor plans during the detailed design phase is typical, but simply too late in the process. Floor layout plans should instead be considered to be part of the preliminary specification and determined well before detailed design begins. You may recall this information from the DCU course Data Center Projects System Planning, where this planning sequence was explained in greater detail. It is not necessary for a floor layout to comprehend the exact location of specific IT devices. This course will show that effective floor layout plans only need to consider the location of equipment racks or other cabinets and to target power densities. These preliminary floor layouts do not require knowledge of specific IT equipment. For most users, it is futile to attempt to specify particular IT equipment locations in advance. In fact, oftentimes racks may ultimately house equipment that is not even available on the market at the time the data center is designed. The reasons that floor layout plans must be considered part of preliminary specification and not part of detailed design include: density is best specified at the row level, so rows must be identified before a density specification can be created. For more information on specifying densities, please consider participating in the DCU course Specifications of Data Center Power Density. Phasing plans are best specified using rows or groups of rows, so rows must be identified before an effective phasing plan can be created. The floor grid for a raised floor and the ceiling grid for a suspended ceiling should be aligned to the rack enclosures, so rows must be identified before the grids can be located. Criticality or availability can be specified differently for different zones of a data center, and rows must be identified before a multi-tier criticality plan can be created. Density and phasing plans are a key part of any data center project specification, and both require a row layout. Detailed design can only commence when density, phasing, and criticality are specified. Therefore, a floor plan must be established early in the specification phase of a project, after concept, but well before detailed design. Most data center floor layout plans are made up of two principal components. The first is the layout of the room itself. The second is the layout of the equipment within the data center. Note that for many users, the room is predefined or pre-existing, and the only option is to lay out the equipment. Any data center user is at a huge advantage if he or she has the ability to lay out the room boundaries, and if the user can influence the structural room layout using the principles established throughout this course. The room layout includes the location of walls, doors, support columns, windows, viewing windows, and key utility connections. If the room includes a raised floor, then the height of the raised floor and the location of access ramps or lifts are also part of the layout. If the room includes a raised floor and/or suspended ceiling, then the index points for the floor or ceiling grid are also critical design variables. The index points selected determine how succeeding floor and/or ceiling tiles are laid out and can have a significant impact on the physical efficiency of the layout. For purposes of this course, room measurements will be described in units of tiles, where a tile is equal to 2 square feet, or 600 millimeters, or 1 standard rack enclosure width. Equipment layout includes the location of IT equipment and the location of power and cooling equipment. IT equipment is commonly defined as a rack or cabinet location without regard for the specific devices in the cabinets, but other equipment, such as tape libraries or large enterprise servers, may have form factors that are different from typical cabinets and must be called out explicitly. In addition, IT equipment in a layout must be characterized by its airflow path. In the case of typical IT racks, the airflow is front to back. But some devices have other airflow patterns, such as front to top. Power and cooling equipment must also be accounted for in the equipment layouts, but many new power and cooling devices are either rack-mountable or designed to integrate into rows of racks, which simplifies the layout. As previously mentioned, several important data center characteristics are affected by floor plans. To understand the effective floor layout methods, it is important to understand the consequences. So let's take some time and discuss each of these layout parameters in more detail, beginning with the number of rack locations. The floor layout can have a dramatic effect on the number of rack locations that are possible. Although on average, the number of IT rack locations possible can be estimated by dividing the area of a data center by 28 square feet per rack or 2.6 square meters per rack. It is important to note that the actual number of racks for a particular data center can vary greatly from this typical value. This concept is further explained in the DCU course, Specifications of Data Center Power Density. The basic principle of floor layout planning design is to maximize the number of rack locations that are obtained. Small variations in the location of walls, existing IT devices, air conditioners, and power distribution units can have a surprisingly large impact on the number of possible rack locations. This effect is magnified when high power densities are required. For this reason, a careful and systematic approach to floor layout planning is required. The floor layout plan can have a major impact on the achievable power density. With certain cooling architectures, a poor layout can decrease the permissible power for a given rack by over 50%. This is a huge performance compromise in a modern data center where new technologies have power densities that are already stressing the capabilities of data center design. In many data centers, users will establish zones of different power density. These density zones will be defined by the floor equipment layout. The floor layout plan is therefore a critical tool to describe and specify density for data centers. The floor plan can have a dramatic effect on the complexity of the power and cooling distribution systems. In general, longer rows and rows arranged in the patterns described in this course simplify power and cooling distribution problems, reduce their costs, and increase their reliability. In addition to impacting the density capability of a data center, the floor plan can also significantly affect the ability to predict density capability. It is a best practice to know in advance what density capability is available at a given rack location and not to simply deploy equipment and hope for the best, as is a common current practice. An effective floor layout plan in combination with row-oriented cooling technologies allows for a simple and reliable prediction of cooling capacity. Design tools can automate the process during the design cycle, and when layouts follow standard methods, off-the-shelf software can allow users to monitor power and cooling capacities in real time. Most users are surprised to learn that the electrical power consumption in a data center is greatly affected by the floor layout. This is because the floor layout has a large impact on the effectiveness of the cooling distribution system. This is especially true for traditional perimeter cooling techniques. For a given IT load, the floor equipment layout can reduce the electrical power consumption of the data center significantly by affecting the efficiency of the air conditioning system. The layout affects the return temperature to the CRAC units, with a poor layout yielding a lower return air temperature. A lower return temperature reduces the efficiency of the CRAC units. The layout also affects the required air delivery temperature of the CRAC units, with a poor layout requiring a colder supply for the same IT load. A lower CRAC supply temperature reduces the efficiency of the CRAC units and causes them to dehumidify the air, which in turn causes the need for energy-consuming humidification. Additionally, the layout affects the amount of CRAC airflow that must be used in mixing the data center air to even the temperatures. A poor layout requires additional mixing fan power, which decreases efficiency and may require additional CRAC units, which draw even more electrical power. A conservative estimate is that billions of kilowatt hours of electricity have been wasted due to poor floor layout plans in data centers. This loss is almost completely avoidable. The existence of the rack as the primary building block for floor equipment layouts permits a standardized floor layout planning approach. The basic strategies are summarized as follows: to control the airflow using a hot aisle, cold aisle rack layout, to provide access ways that are safe and convenient, to align the floor or ceiling tile system with the equipment, to minimize isolated IT devices and maximize row lengths, to plan the complete floor equipment layout in advance, even if future plans are not defined. Once these strategies are understood, the effective floor planning method becomes clear. Let's take some time and explore each of these points in more depth. The use of the hot aisle, cold aisle rack layout method is well known. The basic principle is to maximize the separation between the IT equipment exhaust air and intake air by establishing cold aisles where only equipment intakes are present and establishing hot aisles where only equipment hot exhaust air is present. The goal is to reduce the fraction of the hot exhaust air which is drawn into the equipment air intakes. The basic hot aisle, cold aisle concept is shown here. In the figure, the rows represent the IT equipment enclosures. The enclosures are arranged such that the adjacent rows face back to back, forming the hot aisles. The benefits of the hot aisle, cold aisle arrangement are dramatic as the power density increases. When compared with random arrangements or arrangements where racks are all lined up in the same direction, the hot aisle, cold aisle approach allows for a power density increase of as much as 100% or more without hot spots if the appropriate arrangement of CRAC units is used. Because all cooling architectures benefit dramatically from hot aisle, cold aisle layout, this method is a principal design strategy for any floor layout. It is a legal requirement as well as common sense to provide appropriate access ways around equipment. The hot aisle, cold aisle system creates natural hallways or aisles that are well defined. Since an effective data center is based on row layouts with aisles which are access ways, it is important to identify and understand the impact of column locations. A column could consume up to 3 rack locations when it falls within a row of equipment racks, or even worse, could result in the elimination of a complete row of racks when obstructing an aisle. This illustration shows a room layout with a 4-foot or 1.21 meter cold aisles and 3-foot or 0.91 meter hot aisles and a 4-foot or 1.21 meter perimeter clearance. This room fits 40 rack locations when no columns are present. When a column exists, but aligns with the row of equipment racks, as this image shows, only one rack may be impacted. This clearly illustrates the possible impact on the number of rack locations when columns exist in the room. When a column aligns with an aisle, a more significant impact can occur. This illustration shows the column in the aisle. Occasionally, this may be determined to be an acceptable obstruction if the local authority having jurisdiction believes that shifting the equipment rows and possibly eliminating available rack positions is an unreasonable accommodation according to the local Disabilities Acts. Disabilities Acts across the globe provide guidelines for acceptable aisleways. The local authority determines if reasonable accommodations have been made on a case-by-case basis. For more information and to review some examples of these disabilities, please visit the following URLs listed here. This layout illustrates an attempt at recreating sufficient aisles, but represents a poor alternative since by the loss of 6 racks, the hot aisle cold aisle layout is severely impacted and cooling becomes less predictable. Even more racks are lost when the rows must be shifted so that the column is no longer in the aisle. In this instance, the rack count has drastically dropped from 40 to 29, a decrease of over 25%. The last scenario shows an alternate configuration of racks. With this configuration, 35 rack locations fit, which is much more favorable than shifting rows. Later on in the course, we'll further explain the value of doing both vertical and horizontal layouts to determine the optimal positioning. Typically, a data center layout would be adjusted to place the columns within the rows of equipment where they take up potential equipment locations. The constraint to not have support columns in aisleways is a very severe constraint. It essentially ties the designer's hands and dictates areas that cannot be aisleways. As the layouts previously shown clearly illustrate, it is common that the shifting of equipment rows to accommodate column locations can cause the loss of an entire row of equipment as that row becomes trapped against a wall or other obstacle. Therefore, the careful location of the rows of equipment relative to the columns is of primary concern in the floor layout. In many data centers, the floor and ceiling tile systems are used as part of the air distribution system. In a raised floor data center, it is essential that the floor grid align with the IT equipment enclosures. If the equipment and the grid do not align, the airflow can be significantly compromised. It is also beneficial to align any ceiling tile grid with the floor grid. This means that the floor grid should not be designed or installed until after the equipment layout is established, and that the grid should be aligned or indexed to the equipment layout according to the row layout options. Unfortunately, designers and specifiers often miss this simple and free optimization opportunity. The result is that either the grid is misaligned with the IT equipment, which results in a corresponding reduction in efficiency and density capability, or the IT equipment is aligned to the grid but a non-optimal layout results, limiting the number of IT cabinets that can be installed. The length of a hot aisle, cold aisle system is adjustable in increments of the width of an equipment cabinet, which provides significant flexibility. However, the spacing between the aisles has much less flexibility and is a controlling factor in the equipment layout. The arrangement is always defined for a row pair, and standard pitches exist between row pairs. A pitch refers to a template or standard pattern specific to a particular data center floor plan that defines how rows of racks are spaced from each other. This diagram illustrates this concept of a standard pitch, where the pitch could be repeated throughout the data center. 4 standardized pitches exist between row pairs, which are illustrated here. Each of these repeatable pitches is defined by the number of tiles where a tile is 2 square feet or 600 millimeters in width. Notice that in all 4 pitches, the equipment racks are aligned to tiles in the cold aisles. This is because in a raised floor environment with perimeter-based cooling, full perforated tiles are needed in the cold aisles for air delivery. This pitch shows the most compact geometry of a row pair with a 7-tile overall width and is the most commonly selected building block for data center layouts. However, in some situations, wider pitches become necessary. Once a reference concept design has been selected for a data center, we can use the decision tree, which provides guidelines for when to use each of the 4 pitches. If you'll take a look at your copy of the flowchart, you will notice, for instance, the flowchart illustrates that pitch B is used to provide 50% more raised floor cooling capacity in the cold aisle for higher density applications with raised floor air distribution. Pitch C or D, on the other hand, may be needed if racks with specialized cooling plenums fixed to the back are used. Special row pitch dimensions, which are incrementally smaller than the 4 standard ones, may have an advantage for situations involving a hard floor environment. The 4 pitches previously discussed align the racks in the cold aisle with the tiles for purposes of air delivery through the raised floor. However, when a raised floor is not used, that cooling constraint goes away. For example, consider a scenario where cooling accessories are required on the back of equipment racks for a high-density application. That increases the rack depth from 42 inches to 50 inches, or 1.06 meters to 1.27 meters. Using the minimum 3-foot hot aisle, 4-foot cold aisle, the smallest allowable pitch will now be 15 feet 4 inches, or 4.6 meters. This is an 8-inch increase times 2 rows of racks, or in metric terms, a 0.2 meter increase times 2 rows of racks. When a layout on a hard floor using the floor standard pitches is a problem, i.e. you lose an additional row by a couple of feet or less, the pitch can be compressed. As long as aisle widths remain the minimum of 3 feet or 0.914 meters for the hot aisle and 4 feet or 1.21 meters for the cold aisle. An effective data center floor plan should be deployed in row pairs, using the basic building pitches described. However, there are various barriers and constraints that interfere with the optimal layout. Let's discuss those next. The control of airflow by separating hot and cold air is compromised at the end of any row where hot air can go around a rack and return to IT equipment air intakes. Therefore, the ideal design of a data center is to have no row ends, i.e. rows of infinite length. Conversely, the worst-case scenario is when racks are isolated, i.e. a row length of a single rack. In addition, the ability to effectively implement redundancy is improved with longer rows. The goal of row layout is to maximize row lengths consistent with the goals of providing safe and convenient access ways. In general, a layout that provides longer row lengths is preferred, and a row layout that generates short rows of 1 to 3 racks should be avoided. The first phase of equipment deployment often constrains later deployments. For this reason, it is essential to plan the complete floor layout in advance. Many data centers are fit-outs of existing space. In these cases, no room layout options exist. Although for some data centers, the choice as to where to locate a wall or other options may exist. These options are worth exploring, so an optimal design may be achieved. For data centers in new construction, considerable options are available regarding wall locations. It is a basic and generally unappreciated principle of data center design that the ability to locate walls can greatly improve the performance of the data center. Therefore, when it is possible, the layout of the room boundaries should be chosen based on the standard data center design principles. Let's explore each of these design principles in more detail. There are preferred room dimensions for data centers based on the pitch chosen. Given an area or room that is rectangular in shape and absent of constraints regarding columns, the preferred length and width are established as follows. One dimension of the room should be a multiple of the hot aisle, cold aisle pitch, plus a peripheral access way spacing of approximately 2 to 4 tiles. The other dimension of the room is flexible and will impact the length of the row of racks. When one of the dimensions of the room is not optimal, the performance of the room can be dramatically reduced, especially if the room is smaller. The most obvious problem is that the number of equipment cabinets may be lower than expected because some space cannot be used. The second, less obvious problem is that when the ideal layout is not achieved, the power density and electrical efficiency of the system is reduced. To understand the effect of room dimension on the number of equipment cabinets, we can consider a room with a fixed length of 28 feet or 8.534 meters and a variable width. In such a room, the length of a row would be 10 racks, allowing for 2 tiles at each row end for access clearance. The number of equipment enclosures that could fit in the sample room varies as a function of the width of the room shown here. This image also shows how the number of installable racks jumps at certain dimensions as new rows fit into the room. Certain numbers of racks are preferred because the even row number permits a complete hot aisle, cold aisle pair to be installed. The preferred width dimensions are listed for the pitch and the perimeter clearances defined. The location of support posts within a data center can dramatically affect the equipment layout within a room. Therefore, when an option exists to locate room boundaries, the following guidelines apply. For smaller data centers, arrange the room boundaries if possible so that no support columns are in the equipment area. Rooms should be rectangular where possible. Unusual shapes, niches, and angles often cannot be effectively utilized and/or create a reduction in power density or electrical efficiency. For situations where columns are unavoidable but boundaries are flexible, the floor plan should be laid out as if no columns existed, based on the standardized dimensions of the room and the pitch required. The columns should then be located directly over any one particular rack location, preferably at a row end. For very large data centers, the location of the walls in relation to the columns is typically inflexible. When a phase deployment is planned, a number of special floor layout planning techniques exist that are beneficial. These include creating area partitions and advanced layout of future rows. When a future phase represents a very large degree of uncertainty, area partitions or walls that subdivide the data center into 2 or more rooms can be used. Benefits to this approach include the ability to repurpose areas in the future, the ability to perform radical infrastructure modifications in one area without interfering with the operation of another area, the ability to defer the installation of basic infrastructure such as piping or wiring to a future date. The advent of modular row-oriented power and cooling architectures has reduced the need to provide radical infrastructure modifications during new deployments and has greatly reduced the cost and uncertainty associated with installing base wiring and plumbing infrastructure. Therefore, the compelling need to partition data centers has been dramatically reduced. Nevertheless, retaining options like future repurposing of an area is valuable for some users. The key to successful partitioning is to understand that partitions should never be placed arbitrarily without first performing an equipment layout exercise. This is because the floor layout can be seriously compromised by the poor choice of a partition position. During the setting of partitions or walls within the data center, the same principles should be applied as those used when establishing the data center room boundaries. The standard spacing of rows must be considered. Failure to do this can result in problems as shown here, where the location of a wall has caused row 5 of the equipment layout to be lost, representing 10 racks out of the 80 rack layout, or 12% of the total, a significant loss of space. Although the wall was only offset by a small amount, this loss occurs because the wall-to-wall spacing does not permit appropriate access ways if row 5 is included. Furthermore, the access way between row 6 and the wall has become a hot aisle. This reduces the confining effect of the hot aisle-cold aisle design and will result in a reduced power capacity for row 6. Finally, because the primary access path between row 6 and the wall is now a hot aisle, this creates an uncomfortable zone for personnel. These factors taken together clearly demonstrate how serious a small change in a wall location can be when partitioning a data center. With the existence of the rack as the base building block and the row pair as the guide, a standard floor layout approach is achievable. Starting with a floor plan diagram for the room, the basic principles can be easily broken down into a step-by-step process. The first step in floor planning is to identify and locate all physical room constraints. These include identifying and locating columns. Be sure to verify the exact as-built dimensions. Identifying and locating existing doorways on the plan. Identifying and locating existing fixed equipment in the room, including existing breaker panels, pipe connections, fire suppression equipment, and cooling equipment on the plan. Next, the user must gain an understanding as to what additional equipment will be placed in the room, and they must have an understanding in regard to critical room attributes. Room-level options include identifying additional equipment that must be placed into the room, including any additional cooling equipment, fire suppression equipment, power equipment, or user workstations. If the room uses a raised floor, determining the length of access ramps and identifying all possible options for locating the ramps. It is critical at this stage to know if the facility will have a raised floor. Many new high-density data centers do not use a raised floor, so a raised floor should not be automatically assumed. Sometimes it is even appropriate to remove a raised floor from an existing site for new deployments. For more information on raised floors, please consider participating in the DCU course, Re-examining Raised Floor Applications. Every room has two primary layout axes, or directions that the rows can be oriented, vertical or horizontal. The axis selection is one of the most critical decisions in a data center plan and has a large impact on performance and economy. When using a hot aisle, cold aisle row pair arrangement in the pitch determine necessary or preferred, test the two primary axis orientation layout to establish if either has an obvious advantage. When performing the test layouts, ensure that columns are not located in main axis ways. If no raised floor exists, the rows must be aligned to the grid so that the cold aisles contain complete tiles. Sufficient clearance exists at row ends and between rows and walls. Sufficient clearance or access exists around any fixed equipment in the room. The access ramps, if required, are present and have been optimally located. Any open areas, or areas for another purpose, face a cold aisle and not a hot aisle. Locations have been found for any additional equipment identified previously in the room level options. All row axes face in the same direction, meaning you should avoid perpendicular rows. The entire room is laid out, even if no immediate plans are in place to deploy in sections of the room. To determine the preferred layout, the following factors should be considered. Which layout axis most effectively keeps columns out of main axis ways? Which layout axis fits the most equipment enclosures? Which layout axis works best with the preferred hot aisle, cold aisle pitch? Which layout axis has hot aisle, cold aisle row pairs and does not end up with an odd number of rows? Which layout axis has the fewest short rows or isolated racks? Which is the most aesthetic layout of the data center for purposes of viewing or tours? Different users may weigh the criteria differently. It is common for users to choose a layout axis up front due to aesthetic issues without concern for the data center performance and later regret their choice. The preferred method is to test both axes during planning and deliberately decide the axis selection based on an understanding of the consequences. The process of selecting the primary layout axis typically establishes the row locations accurately. With the row locations established, it is critical to establish and validate the row boundaries. This includes setting the row end boundaries and verifying the boundaries between fronts and/or backs of rows with respect to other equipment, columns, or walls. Access must be provided between row ends and other obstructions using the following guidelines. For plain walls, a minimum of 2 tiles is an acceptable spacing to a row end, and oftentimes larger data centers will prefer 3 tiles to provide better accessibility. For some layouts, it may be desired to end a row at a wall. This typically creates a dead-end alleyway, which may limit the length of the row based on code requirements. For long rows of over 10 racks, local regulations may require that breaks be placed in rows to allow personnel to pass through. This may also be a practical concern for technicians who need access to both sides of a rack enclosure without having to walk a long distance. The spacing between the front row and the back faces must be double-checked to ensure that the access ways are sufficient. It must also be verified that any other equipment that has been located as a part of the floor plan is not constrained by piping, conduits, or access restrictions. The aforementioned restrictions and boundaries must be marked on the room layout, and then the original access selection and row layout confirmed. For small data centers, for example, ones with just 2 rows of racks, this floor planning process can occur as a paper study. As the room size grows, computer-aided tools that ensure consistent scale become necessary in order to accurately plan the floor layout. Ideally, the row layout and boundary areas should also be marked out using colored masking tape in the actual facility. This step is quite feasible for many smaller, fit-out designs and for retrofits, and often identify surprise constraints that were not realized during the conceptual plans. Once the boundaries are established and the axis of the rows set, the enclosure cabinet layout can be performed. This begins with the partitioning of rows by phase. For each phase, multiple zones or areas may exist, each with a unique density requirement. The DCU course, Specifications of Data Center Power Density, provides rules for establishing the preferred and most cost-effective level at which to define density requirements and the preferred increments of deployment. If the data center has a pre-existing raised floor, then the actual location of the floor grid relative to the wall is pre-established and was comprehended in an earlier process. However, for new rooms, the raised floor grid location is controlled by the floor layout. An index point for the raised floor grid should be established in the plan and clearly and permanently marked in the room. It is absolutely essential that the contractor installing the raised floor align the grid to the index point during installation. If this is not done, it may not be possible to shift the layout later to align with the grid due to the boundary constraints. In a raised floor design, this can result in a massive loss of power density capability and a dramatic reduction of energy efficiency. This is completely avoidable and a terrible error that is commonly made during data center installations. Data centers that use a hard floor rather than a raised floor do not have this concern. If the data center uses a suspended ceiling for lighting and/or air return, aligning the ceiling to the index point is also highly recommended, but less critical. Another key item to address in the floor planning sequence is minimizing isolated IT devices and maximizing row lengths. When row lengths are less than or equal to 3 rack locations, the effectiveness of the cooling distribution is impacted. Short rows of racks mean more opportunity for mixing of hot and cold air streams. In rooms that have one dimension that is less than 15 to 20 feet, it would be more effective in terms of cooling to have one long row rather than several very short rows. The final step in the floor planning process is to specify the floor layout for subsequent design and installation phases of the data center project. The specification is documented as a detailed floor layout diagram, which includes all necessary room and obstruction measurements, all rack locations identified, all unusable areas marked, and non-rack-based IT equipment that requires power and cooling noted. Ideally, this specification diagram is created in a computer-aided tool, which then allows for the complete design of the data center's physical infrastructure, detailed to the rack level. Now let's move on and discuss some common errors in equipment layout. Many users attempt rudimentary floor layout planning, yet still have downstream problems. Let's discuss some of the most common problems observed along with some simple solutions. And let's start with the first common error, which deals with the failure to plan the entire layout in advance. Most data centers begin to deploy equipment without a complete equipment deployment plan. As the deployment expands, severe constraints on the layout may emerge, including equipment groups grow towards each other and end up facing hot to cold instead of hot to hot, with resultant hotspots and loss of power density. Equipment deployments grow toward a wall, and it is subsequently determined that the last row will not fit, but could have if the layout had been planned. The rows have a certain orientation, but it is later determined that much more equipment could have been deployed if the rows had been oriented 90 degrees from the installed equipment, and it is too late to fix it. Equipment deployments grow towards a column, and it is subsequently determined that the column lands in an axis way, limiting equipment deployment, but much more equipment could have been placed if the layout had been planned in advance. Equipment deployments get off the standard floor tile spacing. Later, high-density deployments are trapped, not having full tiles in the cold aisles with a resultant loss of power density capability. Most existing data centers have one or more of the problems discussed in this course, with the attendant loss of performance. In typical data centers routinely observed, the loss of equipment locations due to these problems is on the order of 10 to 20% of the total equipment locations. Additionally, the loss of power density capability is commonly 20% or more. These unnecessary losses in performance represent substantial financial losses to data center operators, but can be avoided by simple planning. The analysis in this course demonstrates the criticality of room support column locations. The columns should be exactly located on any floor layout plans to avoid surprises. To compound this problem, many building drawings do not show the correct dimensions for support columns. Actual columns are often built out larger than the original column dimensions during or after construction to accommodate wire or piping chases. Therefore, it is essential to verify the actual column dimensions and not rely on architectural drawings for the building. Many data centers are partitioned for various reasons, including deployment phasing. Often these partitions are added late in the design process and without much forethought. Yet locating partitions to maximize the performance of the data center is a science that requires considerable thought and planning. Columns present such a problem that it is frequently the best strategy to place a partition in line with as many columns as possible. In any case, using the guidance provided earlier in the phase deployment section of the course can help avoid the problem where a partition causes the loss of an entire row of equipment. Now let's wrap up with a brief summary. To summarize, let's review some of the information that we have covered throughout the course. Floor layout is a critical step in the design process for large and small data center projects. When floor plans are not considered early in the planning process, the result is many irreversible compromises to the ultimate performance of the data center, including reduction in IT equipment capacity, reduction in power density capability, and increased electrical bills. Many users assume they can't create a floor plan early in the process because they don't know exactly what IT devices are going to be deployed. This course shows that it is not necessary to identify specific IT devices in advance for most designs, and that most of the benefit of floor planning is independent of the specific IT devices deployed. A proper floor plan is the necessary foundation of an effective density and phasing plan. In fact, density and phasing plans without a floor plan are technically ambiguous and incomplete. By incorporating floor planning into a standard design methodology, the design of data centers can become highly automated and predictable. Thank you for participating.